Hello, everyone. Welcome. Thanks for attending this session. So, our topic today, we're going to explore small and sovereign systems, or let's say domain-specific intelligence, to AI systems on one single 8 gigabyte VRAM system. And basically, what we achieved was due to a very interesting experiment. We wanted to address some of the challenges that we had in with the generic LLMs and training them, budgeting them, and basically addressing cost performance issues. Well, most of us some years ago, or even a few years ago, purchased some devices which by day to day we are using. Most of us are not having those enormous VRAMs and system resources and stuff. So what should we do? Well, I ran the experiment with basically my agents, and which were trained before I run this experiment. And well, it was just one engineer, one laptop, and addressing two problems. The first thing I want to go through is the MOE decoder, which is a mixture of expert diffusion coding model. A tiny model or a tiny toy, we can address it as a tiny toy, which was an multi-step fast training SLM capable of generating more than just code completion or code suggestion. So we know that most of us engineers or developers, we don't need the frontier compute power to get the work done that we want. Maybe many of the generic users, they don't care about the architecture and what they are doing. But since we know what we are doing, the right size and the right measures always accomplishes the requirement. So the result was the result of this experiment was a 10 million parameter coder SLM, and also and another interesting thing that we achieved was training an Armenian text-to-speech and speech-to-text pipeline with utilizing already existing tools. By the way, I cannot speak Armenian. I don't have the domain knowledge, but it's just it's basically what I could have scraped and going into the grammar and finding out how the language works. So the part A of my talk will address training of the mixture of experts diffusion coder. So the 10 million parameter diffuser coder was an achievement of experimenting with GPT-based LLMs. So GPT-based LLMs, or all of us or most of us must know Andrei Karpathy. Anyone? Yeah, sure. So yeah, he released a repository which was addressing how to make a nano GPT and similar approaches, but that sparked some ideas of working on diffusion base and having a customized tokenizer, not a Hugging Face tokenizer, but a super BP tokenizer to achieve masking and unmasking and achieving speed and almost accurate, let's say, result. So we know that most codes live in a narrow world, and code LLMs are enormous, opaque, and costly to run. The infrastructure to host them is pretty costly, and this experiment was targeted to accomplish a front end and some of it, like backend development with TypeScript native languages and its frameworks. So the question was, can a 10 million parameter model on a laptop specialize per framework? And it was able, like what we trained was able to generate code by unmasking, not like the traditional token decoding and like predicting the next one and predicting the next one. So the mask discrete, we use the mask discrete diffusion and not auto regressive methods to achieve this. Also, like the entire flow was stitched together based on multi-layer experiments. I'm going to discuss more and share the code as well. So the result was 9.58 million parameters for experts on one 8 gigabyte VRAM laptop. And the first phase was to train our tokenizer and also introduce the router, which was able to detect like the domain-specific expert and route to the specific destination that the model is required to send the request. So the standard, what went wrong was during our experiment was the standard MOE collapse. Mixture of experts, the experts collapsed midway and we couldn't generate a readable or compilable code. And the router entropy was like pinned at the maximum and we couldn't basically get it working properly. But what basically went wrong was like stitching a load balancing loss to router's Z loss. The cheap supervision basically breaks the collapse. So the cross entropy on the mean router was basically derived from the source repository. We tried to label the source repositories when training the tokenizer and our data set, so that the router understands what is where and what means what. We used basically a composite objective from some research papers from Wang et al. For code diffusion models, plus a two-stage curriculum, which was generic pre-train and following by a fine-tuning. And the result was our four-arm abulation, same corpus, and like the matching ground of the compute. And with our routing, meaning mixture of expert and diffusion on, we were able to basically reach to like perplexity levels that was usable. And like with like the model was also trained with a dense and no mixture of experts variant, and it was unusable. What router was doing across the denoising step was committing more tokens as it was getting unmasked. It was basically committing more tokens. And then it was caching the assignments after like basically getting the entropy and committing all of that. It was caching the steps and skipping ahead, which was basically like achieving the stability that we wanted, usable stability. So this is like the result was not a state-of-the-art small language model or a coder diffusion model. It was just a experiment, diagnostic, and analysis contribution, a recipe that fits into our day-to-day development or developer machines, and like some small tasks that we can basically run on our local machines and get some work done. And the code that I'm going to share with you in a repository is reproducible from like the first step to the last, and you can experiment with it. You can fine tune it. You can change it and experiment with it as you like it. So do's and don'ts. A tiny mixture of experts. I have to say that we need like what we learned from training this was measuring the routing with entropy and specialization, and not only the loss. We don't always need like complex methodologies or complex solutions to basically debug or supervise what is going wrong. We can just use cheap supervision for example, we use repo labels to break the collapse, and we basically decided to isolate the cause to understand like what produces a better, stable, usable result. And also, like in order to like fit it, like we didn't basically chop the model and quantized it to fit into a 8 gigabyte of VRAM. We tried to train it from the ground up to be able to fit into our infrastructure and and machines. So, but we need to be like we need to be honest as well when we are training our models. The result of the training, the benchmarking, and like the results we are obtaining needs to be realistic and usable. So this model can achieve like code generation for small tasks with a huge domain knowledge. Meaning that it can basically understand your entire code base and satisfy your requirements with small code generations, enhancements, and suggestions. But won't replace an engineer. It won't replace a very large model. But well, it's cheap, it's free, it lives in your device. You can fine tune it. You can make it run better and bigger tasks. And the part two of my talk would address what we experimented with the Eastern Armenian language and training a pipeline that is that tends to address and contribute to basically providing businesses, users, or anything with usable, let's say, services or products. So we know that like some languages, Armenian is one of them, are very hard for models to be understood because of their grammar, because of their linguistic system. So what I tried, although I don't have the domain expertise in this, but I used some friends' help to achieve this, and used like already existing technologies with like some tiny tricks and hacks that we could basically achieve Armenian voice model which is basically producing let's say usable results. So for this, I think most of you should have heard about Kokoro, which is a 82 million parameter model, and it just understands phenom tokens, and it's language blind, so it doesn't care what language it is. So this was a good choice among all other models because it doesn't care about what system the language uses. It's not like it's basically language agnostic. So, and every Eastern Armenian phenom already you can map it to basically you can map it exactly to its vocabulary table. And then we used the G2P, which was basically the the tool, the intermediary tool, to write Armenian G2P and be a feeder to the Kokoro model. And the result was an intelligible Armenian with no model retraining. It was just a normal fine tuning. So there were 3 local parts and 1 standard interface. So the user can speak to the platform, and it gets basically, we have a validator step, and then we can route any LLM into the pipeline, and the customized Kokoro with Armenian training data can produce a reply which can be played for the users. And there was a step which we wanted to, like, the result of the previous step was an Armenian spoken, let's say, sentence, but with American English accent. So we couldn't really use it. So the result was using another tool, which is Kanade. So the Kanade is used to convert or take your source audio. You can record a source audio in your native accent, and then basically inject it, brute force it into Kokoro to produce more accent accurate Armenian, Armenian spoken output. So, and what we tried and what didn't work was Vibe Voice. We tried Vibe Voice. It didn't produce really usable outputs. The problem was the accent and the accuracy of the phonemes, and also with the fine tuning, like retraining the entire Kokoro from ground up was an expensive step. I mean, you can still train it on your machine, but it takes much longer. Like maybe for me, it took around 4 days with like multi-step training, meaning it was paused sometimes and then resumed, and it wasn't so usable. So yeah, what we achieved was like with a low error rate. Well, it's relative, but yeah, low error rate or character error rate Armenian Whisper benchmarked output, and well, basically on the like 6 to 8 times of the real time speech to text on the 8 gigabyte of GPU, and the entire pipeline, which again I will share in a future update. We can connect, and just a single script to bring the whole pipeline up without training or anything, and it's measurable, it's reproducible. What we did for this, well, we basically exploited language blind phenome models, IPA, G2P, and also like using voice converter for speaker identity, keeping every component of OpenAI compatible endpoints and all of that, and also like we verified the real audio that used to train and retrain the model, and also it was a local first approach. So and we the don'ts for low resource voice are like, as you can see and read on the board. I'm not gonna go through it, but what we learned was like we shouldn't assume that fine-tuning stage always actually improves this stuff. It didn't. For us, it didn't, unfortunately. So the 2 projects were basically aimed to prove that with the right size and right architecture, you can achieve things that are labeled as myth, or it's advertised as myth. That you need like very expensive hardware to do some like let's say some mid-level work, and like also like the local first, all of us are, or most of us are a bit paranoid about like what AI can do. I'm sure that like you saw that a couple of days ago, you heard about OpenAI's agent breaking into Hugging Face server. So like having your own infrastructure and models into in your own machine helps securing and also keeping your stack cheap, maintaining cheap. So thank you for your attention. I am going to answer your question now, and also for code and the repositories. Unfortunately, I'm not going to be able to like demo right now, but the repository is there, code is there. You can just in your free time, you can go download it and like clone it and use the code however you want. It's open source, it's theirs. Thank you. Thank you so much. Thanks.
Okay,
Thanks
we
for your
have
attention.
5 minutes for Q&A, please.
Okay, hi, thank you. So first question about first project. Why is this exact choice of the architecture? Why not just small language model? Why mixture of experts? Why this combination? And also, in addition, like, what did you mean by routing? I just don't understand terminology. What was
Sure.
the routing part?
Thank you for the question. So the reason of mixture of expert was so for dense models, when you're training dense models need more generic data and more supervised training. Meaning when you are picking your data sets, you need to label them properly. You need to train them in a specific way, which is by its nature, let's say, more expensive to train. And also, they don't understand that, for example, I'm sure you've seen it, like you're asking something from generic LLMs. You're asking something like React related, but it generates like some other frameworks. Or you're asking some JavaScript code, but it forcefully generates something like TypeScript. You need JavaScript, it gives you TypeScript. You want something in HTML, but it forces you to use React. So the reason of the router itself understands what is the requested language and its frameworks. So when you're asking, okay, I need this, like in front end, we have React and React Native. Yes, the backbone is the same, but their characteristics, their nature is different. So you need a smart supervisor to say, okay, this is React Native. So I am going to delegate this task to the trained expert to satisfy the requirement.
Yeah, thanks. And each expert is a separate model trained separately.
So the beauty of it is, imagine that you have a bucket, but you are dividing your bucket, and on top, there is the supervisor router. So each one is trained on top of your base. The core or base is TypeScript, which we did was TypeScript. TypeScript was the base, basically expert. Then we added the frameworks in the router, so it understood that, okay, in the domain of TypeScript, I have this like frameworks. Yeah.
Okay, maybe one quick question.
Yeah, one quick question. What is G2P? What is IPA?
G2P and IPA, these are like tools that you can basically train a voice model based on its wavelength. It understands the audio wavelengths, and you can feed it into an audio something like a multimodal model that understands audio and vision and text. So Kokoro is an audio model. It produces audio results. G2P is the tool that you can use to take out any language's phenoms and then feed it into the model. So the Kokoro is a language blind model, by the way. G2P helps that language blind understand the language. It extracts all the wavelengths and everything, the phenomes, the characteristics, and injects it into the model.
Okay, I think that that's it. Let's thank you.
Thank you. Thank you so much. Thank you. Thank you.